Hello, everyone. Today we will delve into Section 3 of Chapter 2, Asymmetric Cryptography. In the previous lesson, we covered symmetric cryptography, and now we will move on to asymmetric cryptography. The principle of asymmetric cryptography is that both the encryption and decryption algorithms and the public key do not need to be kept secret. Only the private key must remain confidential. In contrast, with symmetric cryptography, the key needs to be kept absolutely secret. The main advantage of asymmetric cryptosystem model is its higher security. The public key is openly available, while the private key is kept by the user to ensure confidentiality. Furthermore, compared to symmetric cryptography, asymmetric cryptography allows for digital signatures, non-repudiation, and integrity protection. The downside is that, compared to symmetric cryptography, asymmetric cryptography is slower and takes more time for encryption and decryption, making it suitable only for encrypting small amounts of data. Common asymmetric cryptographic algorithms include RSA, which is based on the difficulty of factoring large integers. Elgamal is another example, relying on the discrete logarithm problem, as does ECC, which is faster and more efficient than RSA. DSA is a variant of Elgamal, and it is the US national standard for digital signatures. However, it can only be used for digital signatures and not for data encryption or key exchange, and it is slower than RSA. Other algorithms include knapsack cryptosystem, Rabin cryptosystem, and Diffie-Hellman, which we mentioned in the previous lesson when discussing key distribution. Let's focus on the RSA algorithm, as it is a classic example of asymmetric cryptography. RSA was proposed by 3 scholars from MIT, and the name RSA comes from the initials of their last names. RSA was first introduced in 1977. The key establishment process in RSA involves several steps. 1. Each user generates a public-private key pair through the following algorithm. First, 2 large prime numbers, P and Q, are randomly chosen. 2. Compute the modulus n equals P times Q and phi n equals P minus 1 times Q minus 1. 3. Randomly choose an encryption key E, which must lie between 1 and phi n. 4. Solve the equation ed congruent to 1 modulo phi n to find the decryption key D. In asymmetric cryptography, the most important aspect is keeping the decryption key D secret. The final public key is E, and the private key is D. When using RSA for encrypting the message M, the sender must obtain the receiver's public key E, since the public key is openly available and does not need to be kept secret. The sender then computes the ciphertext C using the formula M to the power of E modulo n. Upon receiving the ciphertext C, the receiver uses their private key D to recover the plaintext M by calculating C to the power of D modulo n. Let's go through an example. First, we randomly choose 2 prime numbers, P equals 17 and Q equals 11. Using the formula, we compute N equals P times Q, that is, 17 times 11 equals 187. Next, we calculate phi n equals P minus 1 times Q minus 1, that is, 16 times 10 equals 160. Then, we randomly select a public key E, which must be a prime number, and choose E equals 7. Finally, we calculate the private key D using the formula DE equals 1 modulo 160, which gives us D equals 23. Since E equals 7 and D equals 23, we verify that 23 times 7 equals 161, and 161 modulo 160 gives a remainder of 1, satisfying the 5th equation. Thus, we have our final RSA system. The public key E equals 7, and the private key D equals 23. Now, let's go over the RSA encryption and decryption process. Suppose we have a plaintext message M equals 88. Note that 88 must fall within the range of P times Q, meaning it must be less than 187. To encrypt, we calculate 88 to the power of 7 modulo 187, where 88 represents the plaintext message and 7 is the public key, which results in a ciphertext of 11. To decrypt, we compute 11 to the power of 23 modulo 187, which results in 88, recovering the original plaintext M equals 88. This completes the encryption and decryption process. That concludes our lesson on asymmetric cryptography. Thank you.